So in this particular lecture, we are going to cover the topic of hydrostatic pressure. That's very, very useful in aerospace, in aerodynamics, aerospace industries. Before we start, let's consider the case. I wanted to consider that there is a point. Okay, let's say, I got the wing of the airplane, just to use as an example, and from that particular wing, I'm going to take one point. Now, that particular point, let's assume that point can be modeled as a cube, okay? And I can take that small element, it's a differential element. This is an infinitesimally small element. It's basically a point. So we take this element such that your volume actually tends to zero, okay? When it tends to zero, this becomes a point. And these forces acting on this surface keep this body in balance. You can see that if I have sigma xx on this side, you have sigma xx on this side. These are the shear stresses, all the normal and shear stresses are acting on my body. Okay, and based on this, if I wanted to find now my loads, I just multiply the area times that stress, and will get the stress I'm looking for. Okay, so we know for a fact that, and we covered this last time, the total force will be the force in my surface forces, plus my body forces, right? And I told you that your body forces are nothing else than weight. This is weight. And this is surface. Okay? So your problem, the way it works is, what if on this side I have a pressure, okay, because the body is a fluid, right? That small element, what happens on one side should be slightly different what happens on the other side. So what you can see is, if this pressure is acting on this side is acting on the opposite side to keep it in balance. That's why this is in the J direction, but this is the Y direction. This is minus J, because it's balancing out this other pressure. Okay, so now think about the same idea as this point. This is a point, and I'm exaggerating that point. I'm taking the delta x, but it's really dx, where dx is nothing else. So dx is nothing else than delta x approaching to zero. It's basically a point. Okay, so if I was going to do everything in the x direction, let's say, I could say that on one side, if you would, right, I have p, and then my p plus dx, that the variation, I go from one point to another point. I have a fluid there, and I have a fluid here in the x direction. I have the same fluid, and I take an element there. The pressure here would be p x plus dx. The pressure here will be p of x. And then I can use Taylor's series expansion to say p plus partial of p respect to x, d of x. And if I subtract this minus this, I get the following equation. And I can do this in this one direction. I can do this in every other direction possible. Okay, so this becomes very, very important in the derivation and the analysis that we are about to do in a few minutes. But before we do that, let's just get started here. So this is pressure. Okay, I don't want pressure. What I really want is area. I want force. See, I want force. So if I want force, that means that my total force will actually equal to my pressure times area. Okay, so if I am acting, let's say, on this face, in the x phase, right? This is the x phase. The area would you agree that the area is dy dz, right? Dy dz, that's the area in this space, on this space, at that space. So basically, I want to convert all these guys to area, so I multiply this by dy dz on both sides, dy dz, and this one I multiply by dz, because in the x, this plane is dz. In this plane is dy dz. As you can see that when it's in z, it is this area dy dx. dx dy. Okay, and if you realize now, all of these are identical. You see, they're completely the same. So what I could do now is I could add all this up, and I can and put it in vectorial notation, and I can say the small differential area of the, let me change my colors, is equal to minus partial of p respect to x dx dy dz in the I direction minus partial of p respect to y dx dy dz in the j direction minus partial of p respect to z dx dy dz. Okay, so now what I could further do in the problem is I could, if you realize they're all the same, right, then I can factor them out. So I can say, and by the way, this small subscript here, many books use the arrow on top of it to express a vector. I use a underline. That's what it means. It's a vector. So it's minus partial of p respect to x, I minus partial of p respect to y, j, sorry, plus with the minus sign is already there, partial of p respect to z, k, dx, dy, dz. Okay? And if you recall from calculus, your operator lambda was nothing else than, this is a vector as well. This is nothing else than partial of x plus partial of p respect to y partial of z. And what this does is, it takes the gradient. This is nothing else than the gradient. Have I and j missing there. This is nothing else than the gradient of whatever quantity. You see, in this particular case, it is saying it's the gradient of p. You can see the p is there, right? So if I factor out p from this equation, if I took this p out, I'm going to take this p out, going to take this p, going to take this p, and if I factor it out, then I'll get something like this. Okay, so this whole thing is same as minus dx dy dz. Okay, so now also the body force. So this was only for the surface. The variation on your body force g against a vector is going to equal to rho times g, the vector g, dx dy dz. Why the vector? Because g can have acceleration in x, in y, and in z. Okay, it's a vector that has acceleration in all those directions. Okay, so my total force, now my total force F has to equal to my total force acting on the static plus total force acting of my body forces, all has to equal to 0. This is because the body needs to be in equilibrium. Okay, Newton's second law, everything, sum of forces must be 0. Same applied to fluid. It's a Newtonian fluid. We believe that when we call Newtonian fluid, it's because all your properties are a function of the Newton's law applied to that fluid itself. Okay, so if I take all this and we replace all these quantities now, we find that what we get is this is equal to minus P plus rho G dx dy dz is equal to 0. And this is a vector, don't forget this. And this is also a vector. So for this to be equal to 0, the only possible way that can be 0, this cannot be 0. Otherwise, I would not have the small infinitesimal element. That would be a trivial solution, not have the fluid in the first place. Then I would take this equal to 0. So this is the hydrostatic equation that we have been, that's very, very useful in our problems. And let me just show you different variations of these equations. That's probably a lot easier to break it down in different. So this is a vectorial notation. But I could break this down in the x direction, and it will look something like this: minus p variation of x plus rho g of x. And in the y direction is minus p variation of y plus rho, equal to 0 in the y direction. And in the z direction, this is minus p variation of z plus rho in the z direction is equal to 0. Now, if you realize that the gravitational force only acts in the z direction according to our coordinate system, then these go to 0, right? And this is equal to g. Then your equation basically becomes partial of p respect to x is equal to 0. Partial of p, this is pressure, by the way, respect to y is equal to 0. And this is partial of p respect to z is equal to minus rho g. And I should say it's minus rho g because this is minus g because it goes in the opposite direction. Okay, so now if we keep moving, we can further, we can work with this equation and we can find some useful relationships that we use very often. Let's say for an incompressible fluid, we could go ahead and take this equation and say this is z is equal to minus rho g, and we could multiply both sides by dz, and we could integrate this on both sides, and that would give me P2 minus P1 is equal to minus gamma zeta 2 zeta 1. And that would be the very convenient equation that we have been using actually. That's P1 is equal to P2 plus gamma times height. Or sometimes we can also write it H is equal to P1 minus P2 over gamma. This equation becomes very, very useful, especially when the gauges, when we are studying, we are trying to understand how gauges work. Um, so uh, for before we move on, let's see what happens for compressible fluids. Okay, this is for incompressible fluid, and this will be for compressible fluid. Okay, for compressible fluid, this is equal to dP dz. Again, the same. The only difference now is note that this is, I'm going to use this, the ideal gas approximation. So this becomes P RT times G, and then dP over P minus G over R dz over T. And you can see that it's going to give you a similar equation that we previously got, and this is nothing else than your standard atmospheric properties. Okay, from here is where we get the equations for standard atmospheric properties that we talked in the first and second classes. Okay, so how does this equations actually, how we put together, how do we put all this stuff together? This is very, very important in aerospace structures, in aerospace, in aerodynamics, sorry. And basically it's used a lot in the pressure, when we are doing pressure measurements. All your aircrafts have a lot of sensors, okay? And they're constantly taking pressure, they're taking the velocity, they're measuring all that. So how do we really do that? Well, one way to do it is what we call the pitot tube, but we'll talk about that later. But basically the basics of that is something like this. Let's suppose we have this, okay? And this is at gamma 1, and I have a pressure 1 here. And I know here, this is my, somewhere here. Okay. Okay, so let's suppose this point is corresponding to a point here, and then we have this point over here, and this is the distance from here to here is h. Let's tell h1, and let's suppose this is full of a different fluid inside here, and this fluid is gamma 2. Then this is atmospheric pressure in this point right here. So the way we will find the total pressure is here at the center line, this pressure will be P plus H1 times gamma 1 minus, this is delta H times gamma 2. Okay, remember gamma is nothing else than rho times G. So I'm actually using a pressure here. This is equal to 0. So your P at the center line will equal to delta H times gamma 2 minus H1 gamma 1. That's a direct application on how we do this. We usually care for, if I knew the pressure here, I can find the pressure there by just taking that small delta. Okay, so this is some applications of these problems. Let me give you an example of how this could possibly work. Consider the following case. Consider this case. So let's suppose this is point A, point B, point C, point D, and point E. Now, I should point out that maybe this would be a different color. This is a different fluid here. The fluid is different in this section. All of this is exactly the same fluid. This is air. And everything else is the same fluid. Okay. Now, if I told you, so because of what we study right now, I can tell you that the pressure at A has to equal to the pressure at B, has to equal to the pressure at C. However, it's not equal to pressure at D. Why? Because this is all the same fluid. Okay, since it's all the same fluid, I can say the pressures here and here will be identically the same because we look for absolute pressure. However, here my gamma is different, okay? Because gamma is different from this gamma. If I call this gamma 1, call this gamma 2, and I call this gamma 3, these pressures are different. So therefore, this is not equal to D. And this is a different compartment. They don't share. If there was a hole here, and I could just transfer the pressure from one place to another, that will be a different story. However, then I can say that none of these are the same. However, these two are the same. Okay. And if I was to say, what happens if I want to find everything, let's say another point down here, right? Let's call it point I, J, K, L, and M. In that particular case, I can say the pressure at A, J will equal to pressure at J, will equal to pressure at K, will equal to the pressure at L, but it's not equal to the pressure at M. Why? Because again, the pressure here cannot be balanced out. There's no way, there's no connection between them. If I was to create a small hole there, then I could say that this is gamma 1. Then I could say it's the same, right? Although this is gamma 1, but this gamma 1 has a different property because it has a different pressure and different, it might have it not necessarily follows the same pressure distribution as this. I cannot have the absolute value, okay? So this is kind of how these problems actually work. And this is for hydrostatic case. We basically started the problem. We did a free body diagram. Really, I'm sorry for all this derivation, but at the end of the day, these are the equations that we really care for. And this last equation that becomes very, very important for incompressible fluid. For incompressible, H is equal to delta P over gamma. For compressible fluid, as we did in class, then we used this equation and we were able to show that for standard, and we get the same properties for standard atmospheric equations that we got previously. And then I told you how the instrumentation kind of works. And this concludes this lecture on hydrostatic pressure.